Hello, this is Mr. Menchaca. I'm your Physics 1402 instructor for this summer session. I've been asked by Dr. Wuku to start at Chapter 12, the Laws of Thermodynamics. You're going to hear a dog barking, maybe several dogs barking throughout the lectures. You're just going to have to ignore them. I can't shut them up. Let's get started with the lecture. Oops, I guess I need to share the screen. And let's go to PowerPoint. And let's get started. All right. I'm still here in the corner. We're going to talk about the laws of thermodynamics. In this topic, we will explore the laws of thermodynamics. You will find that the first law of thermodynamics tells us that we can increase the internal energy of a system by either adding energy to the system or by doing work on it. That means the internal energy of the system, which is just the sum of molecular kinetic and potential energies, can change as a result of two separate types of energy transfer across the boundary of the system. The second law of thermodynamics constrains the first law by establishing which processes allowed by the first law actually occur. For example, heat energy never flows spontaneously from a cold object to a hot object. Oop, got my notes. Okay. Energy can be transferred to I better switch slides. Energy can be transferred to a system by heat and by work done on the system. In most cases for us, the system will be a volume of gas, which is important in understanding engines. We will assume all gas volumes are in thermodynamic equilibrium so that every part of the gas is at the same temperature and pressure. Let's take a look at the figure. Here, a gas is contained by a cylinder fitted with a movable piston. The gas is in equilibrium, occupies a volume V, and exerts a uniform pressure P on the cylinder walls and the piston. The gas is compressed slowly, so the system remains essentially in thermodynamic equilibrium at all times. As the piston is pushed downward by an external force F through a displacement delta Y, as shown in the right-hand figure, the work done on the gas is given by this equation. The work is equal to minus F delta Y equals minus PA delta Y. So the force is the pressure times the area. Okay. The magnitude F of the external force is equal to PA. This is possible because the pressure is the same everywhere in the system. Notice that if the piston is pushed downward, delta Y is negative. So we need an explicit negative sign in the expression for W to make the work positive. The change in volume of the gas is delta V equals A delta Y. So we can write the work equation as shown here. The work done on a gas at a constant pressure is given by minus P delta V, where P is the pressure throughout the gas and delta V is the change in volume of the gas during the process. If the gas is compressed, delta V is negative, and the work done on the gas is positive. If the gas expands, delta V is positive, and the work done on the gas is negative. The work done by the gas on its environment, W, E, and V, is simply the negative of the work done on the gas. If there is no change in volume, the work is zero. Our definition of work in this equation specifies work done on a gas. In our course, work done by a gas is denoted by W, E, and V. In every case, W is equal to minus W, E, and V. So the two definitions differ by a minus sign. The reason it's important to define work W as work done on a gas is to make the concept of work in thermodynamics consistent with the concept of work in mechanics. In mechanics, the system is some object. And when positive work is done on that object, its energy increases. When work W done on a gas, as we define it here, is positive, the internal energy of the gas increases, which is consistent with the mechanics definition. In the figure on the left, the man pushes a crate doing positive work on it. So the crate's speed and therefore its kinetic energy both increase. In the figure on the right, a man pushes a piston to the right, compressing the gas in the container and doing positive work on the gas. The average speed of the molecules of gas increases, so the temperature and so the internal energy of the gas increase. Doing work on a crate increases its kinetic energy. Doing work on a system of gas increases its internal energy. Come on, there we go. Okay. The equation shown can be used to calculate the work done on the system only when the pressure of the gas remains constant during the expansion or compression. This type of process is called an isobaric process. Iso meaning the same, baric meaning pressure, so isobaric meaning the same pressure process. It's a process where the pressure doesn't change. The figures of a pressure versus volume graph, or PV diagram, of an isobaric process. The curve on such a graph is called the path taken between the initial and final states, with the arrow indicating the direction the process is going. In this case, from larger to smaller volume. The area under the graph is given here. The area under the graph in a PV diagram is equal in magnitude to the work done on the gas. This is generally true whether or not the process proceeds at constant pressure. Just draw the PV diagram of the process, find the area underneath the graph and above the horizontal axis, and that area will be equal to the magnitude of the work done on the gas. If the arrow in the graph points toward larger volumes, the work done on the gas is negative. If the arrow on the graph points towards smaller volumes, the work done on the gas is positive. Whenever negative work is done on a system, positive work is done by the system on its environment. The negative work done on the system represents a loss of energy from the system. The cost of doing positive work on the environment. Okay. The next section will go on with the first law of thermodynamics.